everyone, welcome to this meeting, to this webinar. Today's speaker is Salim Rahal. Said received his PhD from University of Alberta in 2021. He joined HEC Montreal in June of the same year and has been working on a MyText project in collaboration with Hydro-Quebec, with Jean-François Cordeau, Yusri Adouliasak, and myself. He works in the domain of optimization under uncertainty. The topic of today's talk is decision rule-based methods for multistage adaptive optimization. And without further ado, Said, the floor is yours.
Thank you, Okan, and thank you, GERAD, for inviting me to present my work or part of my work during my PhD in one of their Meet a GERAD Researcher series. So to start, I'll start with the outline. I'll have 5 main points, starting with an introduction, then talking a bit about multi-stage adaptive optimization, the methodology of decision rules-based methods, and then I will talk about one of my early research work in which is a hybrid decision rule computational study, and an application of decision rule-based methods in the steelmaking and continuous casting scheduling, basically a production scheduling problem. Then I will end with a few points, or conclude with a few points. So decision making is basically inevitable at different hierarchies of the of any operation, in fact, starting from measurement and sensing, which happens at the level of seconds and milliseconds in terms of time, up to unit operations, which happens at the scale of seconds to minutes. The plant-wide optimization happens at the scale of minutes to hours, sometimes days, up to planning and scheduling, which happens in the scale of weeks to months. So basically, the planning and scheduling levels are the kind of I would say the common part between process system engineering and operations research. In all these levels, we have uncertainty, whether it is from the models, basically some errors in the estimated parameters, empirical models, or the process itself, or even external factors like customers' demand, fluctuation in price, and stuff like that. Depending only on deterministic optimization, which basically neglects this uncertainty, or maybe approximate the uncertain parameter using a nominal value, it will lead to a suboptimal solution, or sometimes infeasible. Maybe the failure to satisfy a certain demand, or the failure to basically maintain a certain safety requirement. Okay, so adaptive optimization, it's a framework that incorporates uncertainty in the decision-making process, and it does so by classifying the decisions into 2 main parts. The first part, known as static decision, which are independent of the uncertainty, and they are known as the here and now decisions. Basically, the lay term for them is here and now. The second group is known as recourse decisions, or adaptive decisions. Based on their name, they are dependent on the uncertainty, and they are also known as wait and see. The 2-stage setting in adaptive optimization basically assumes that your uncertainty will be revealed once and for all. So you first apply the static decision, wait for the uncertainty. Once it is revealed, you either kind of, between quotes, clean the mess of the uncertainty, or you work on the profit based on your static decision by implementing X sub 2, which is the recourse decision. From my point of view, I like to organize the modeling flow or process into 3 main elements. First, I usually start with uncertainty characterization. Okay, how it is represented. We need to address this thing called uncertainty. How does it look like? Then the risk measures. Okay, fine. We want to optimize our decisions based on what? Based on a cost function, cost metric, and this cost metric has to be quantified because it is uncertain. And the final element is basically the solution technique based on decision rule-based methods. As for uncertainty characterization, source we already talked about. We have the description and type. In terms of description, 2 popular ones are the set-based form. Basically, when we describe the uncertainty in a basically closed convex form, whether it is an interval or a deviation from an average point, or maybe a polytope or an ellipsoid. And the other form is using moment-based information from the distribution. So whether it's a first moment, second moment, and stuff like that. In a decision rule based context, I mostly used the first description type, which is the set-based. So I assume that the uncertainty belongs to the closed convex set. As for the uncertainty type, it's a term coined by John Spratton. I'm not sure if I pronounce his name well, and it is based on the dependence of the uncertainty on a decision being made in the decision-making process. So endogenous uncertainty, it depends on the decisions, like its presence or its its presence depends on the decision. Let's say, such as the uncertainty of a size of an oil well. So if you do not drill the oil well, so you will not have this uncertainty. In a logistics context, we can say about the disruption of a facility. It's more or less an endogenous uncertainty, because if you do not open that facility in this location, this uncertainty will not be present in your decision-making problem or process. The second type, which is, I would say, most common, is the exogenous uncertainty, which is independent of any decision you make throughout. One very common external factors are a common example of such uncertainty. Basically, uncertain demand, uncertain price, and stuff like that. The risk measure, what does it do? It basically quantifies the uncertainty, or let's say it maps your objective function from the uncertainty set C to a scalar value R. And in the literature, like coherent, there's this term known as coherent risk measure, which kind of preserves the convexity of the problem, and it has some axiom, other like basically good axioms for complex optimization. The three main types of coherent risk measures that I worked with are first the expectation measure, which is used in stochastic programming. Basically, we are minimizing the expected second stage cost. It requires the knowledge of the probability distribution, and it is risk neutral. So basically, it does not give any feedback about the extreme cases of your decision-making process, which may end up to be very important, especially in safety environmental cases. So that's why we have the second risk measure, known as used in robust optimization, and known as the worst case scenario. So we are minimizing the worst case cost. In this case, we only need to know the uncertainty set without any kind of information of the distribution. So no historical data is required, but the solution is conservative. So here we have two risk measures at kind of two extremum. In the stochastic programming, it's not conservative, but we do not have any clue about how risky it is. In RO, it is very safe. It's immune to any type of risks, but it's very conservative. Conditional value at risk provide a trade-off between these two extremum. It first appeared in the financial industry, and you can see why is that the case. If you use SP, you are unaware of the extreme cases, which is not that good. And RO is very conservative, not good for kind of investments. And basically, what does it do? It is based on a parameter alpha, which basically dictates your tail of a distribution, or basically your kind of worst case scenario, and it minimizes the expectation of that tail. SP and RO, they are special instances of conditional value at risk, where in the first case, an SP alpha is equal to 0. So the tail is the entire distribution, and alpha equal to 1 is the tip. So in this figure, we see the probability density function of a cost function at the left, and the cumulative distribution at the right. So when alpha is equal to 1, so it's similar to RO. When alpha is equal to 99%, we start to see the tail of the distribution and the expectation of the tail. at 95%. So basically, what's the good is that now you have a risk, a feedback about the risk, like how bad it can go, and it is not as conservative as RO. And here, when alpha is equal to 0, it's same as the SP. Multi-stage adaptive optimization is the case where the uncertainty is gradually revealed. Mostly, this is very common in the case where you're taking a decision across a period of time, a long period of time. And once the uncertainty reveals, once part of the uncertainty reveals itself, you take a recourse decision afterwards. Your recourse decision has to follow something called non-anticipativity property, which basically it must only depend on the past revealed uncertainty, cannot depend on any type of future uncertainty. In my work, I worked with multi-stage linear formulation. In some cases, I included discrete values, but the two main assumptions is that one, I assume fixed cost coefficients. They're not variable, and I assume like fixed recourse matrices, so kind of to avoid non-linearity in the uncertain parameters. And in this case, the uncertainty is mainly present in the right-hand side of the constraints, like in B sub t. Okay, so what's the issue with model 1? The presence of the uncertainty set induces or generates what's known as semi-infinite constraints, basically, which are basically the set contains infinite number of points. This infinite number of points will lead to infinite number of constraints, which are basically computationally intractable. So the optimal solution cannot be obtained or recovered. The policies, optimal solution of the policies cannot be obtained or recovered in a finite amount of time. So here, assume that the true solution is kind of some kind of a piecewise function. What is usually done in the literature, that they say, okay, fine, we approximate the uncertainty set using discrete scenario, and we solve a scenario-based optimization. So basically, this approach is common for stochastic optimization in particular. And to recover the optimal solution, we need a large number of scenarios. And here, this is one of the drawbacks of scenario-based approximation methods. Alternatively, what decision rule-based methods proposes is that, okay, fine, we assume that the policy, the recourse decision, will follow a certain form or a certain dependence on the uncertainty. Here, let's say I assume it follows a linear decision rule. And by doing that, we restrict the recourse decision to a function of the uncertainty, and we use some tricks or some theory, some strong duality theory, to construct the tractable counterpart, or to circumvent or overcome this computational intractability. As a mean of illustration, consider we have this generic constraint at stage t. So x sub 1 is the static decision, and x sub t as a function of xi is the recourse policy. And our uncertainty set is a polytope. Yes, you see. Yes, Jean-Francois.
Yeah, sorry to interrupt you. Just a quick question of clarification. So what distinction do you make between classical multi-stage stochastic programming and multi-stage adaptive optimization? So what does the word adaptive characterize here?
Okay, the word adaptive, it was first coined like in the context of using a policy or a decision rule, not, let's say, in the community of scenario-based optimization. What the word adaptive, it mainly means, not only, mainly means that we have two sets of decisions. One of them is static and the other is adaptive. The adaptive is the one that depends on the uncertainty. So in the context of scenario-based optimization, it will be those decisions that are defined over the discrete scenarios.
Okay. Okay.
So back to the question, like, what's the difference between classical multi-stage stochastic optimization, scenario-based stochastic optimization, and multi-stage adaptive optimization? From my from my point of view, I would say that the term was not used in the context of scenario-based optimization. So the comparison may not be like, the difference may not be very clear because the term was not coined in the community of scenario-based optimization.
Mm-hmm. But some of the methods for multi-stage, so classical multi-stage stochastic programming also allow you to have solutions that depend on the realizations of the uncertainty at the different stages. So you could say that some of that belongs to adaptive methods, right?
Yeah.
Okay,
yeah.
It just has a different origin. Okay.
Yeah,
Thank you.
exactly. Yeah.
Okay, thanks.
In a few slides, I will talk about the origin of decision rule-based methods and this term. So here, as a mean of illustration, we show like a simple generic constraint, and the uncertainty set is a polytope. So we define the approximation, which is LDR with an intercept x sub t and subscript mod and a slope for the uncertainty. The observation matrix is to maintain or to make sure that we only depend on the past realized uncertainty. So here the trick is to introduce a redundant min operator into this primary problem. So we're saying that, okay, fine. What we will do is that we will make sure that this constraint is feasible for the worst case scenario in terms of feasibility. And then, because if it is feasible for the worst case, then whatever the uncertainty is, it will remain feasible. Then this is LP, we construct the dual. So now with the dual, we have the dual variable, and now we have the max operator. We implement the same trick by removing the max operator, because basically if the same context is basically if you remove the max operator, we have the tractable counterpart. So basically if the tractable counterpart is feasible in your problem, then the dual problem, which is with the max operator, will be also feasible. So it's kind of a trick that has to do with the feasibility. So once we do that, the semi-infinite constraint induced by the uncertainty set in the problem basically is resolved. So all constraints now are basically deterministic. Okay, but okay, what's the I would say the dilemma, or what's the basically, I would say the dilemma with any approximation technique. So the LDR, they are attractive in terms of so they were first introduced in 2004, and this was kind of the beginnings of decision rule-based methods. It has attractive algorithmic features, but its approximation quality for most problems is poor, is not that high. So now we have this kind of dilemma of, okay, approximation quality as a function of computational cost. Later on, some nonlinear decision rules were implemented, like quadratic decision rules, or quadratic dependence, and polynomial decision rules. Oh, okay, it improves the approximation quality, but now the computational complexity in terms of the nature of your tractable counterpart will start to increase. For example, let's say linear decision rule with a polytope will give you a linear tractable counterpart. Now, linear decision rule with an ellipsoid will give you a second order conic counterpart. Quadratic decision rules and polynomial decision rules will give you second order, will give you like conic and semi-definite counterparts. So the idea is this, like, okay, we're getting better approximation quality, but the cost is also ramping up. So kind of it may not be that favorable for scaling. So a good kind of workaround is the idea of lifting the uncertainty space, or proposed by Andrea Giorgio in 2015. So the idea, or the main idea, is this. So the uncertainty set is lifted, and then in the lifted space we implement a linear decision rule to basically exploit the algorithmic features of linear decision rules. But the LDR in the lifted space has a correspondence to a family of nonlinear decision rules in the original space. So now we're kind of exploiting the best features of the two worlds, which is good or competitive algorithmic features and good approximation quality. And the way the lifting operator is was defined by Giorgio is using the breakpoints. Basically, breakpoints are the points where the change of slopes occur, and the lifting operating is basically consists of min max operator and this breakpoints, and the retraction operator is just the summation. So here, like as an example, assume your uncertainty is a scalar and you have one breakpoint or two linear segments R1 equal to 2. So your lifted space is now R2. We have two lifted elements, so C11 prime and C12 prime. So what you see that C11 prime is proportional to C1, the original uncertainty in the first linear segment, while the C12 prime is proportional to C sub 1 in the second linear segment. So that's how the now LDR in the lifted space will give you a piecewise linear decision rule with two linear pieces in the original space. So here, here you had a small kind of issues that the lifted uncertainty set, the exact set, is not convex. So what Giorgio did, he proposed a polyhedral convex hull. So in this figure, we see that assuming a scalar uncertainty that belongs to a line segment L and L sub I and U sub I. So if we introduce one breakpoint, we'll have the lifted uncertainty set in the second figure. So the bold line is the exact lifted uncertainty set, and the shaded region is the convex hull. So basically, this is the lifted set and the convex hull for the example shown above. And in the third figure, this is the case where you have two breakpoints, or the lifted space is equal to R3. So that's the kind of convex hull of the lifted uncertainty set. Okay, so now, what's the idea of all of this? And the idea was, since the decision rule-based methods in back in my group was very new, the idea was to explore this domain and do some experiment. And the first experiment was done using a multi-stage Newsvendor problem, a classical problem where the idea is to meet the uncertain demand at minimal cost, and we need to optimize the implementable ordering policy X sub t. We have two state policies, inventory and backlog, or storage and backlog, and we have to minimize the cost of ordering inventory and backlog. And we have the, or let's say storage and backlog, and we have some like the known constraints. So here, at first a simple experiment was done with 4 time stages and 3 different decision rules: LDR and PLDR with one breakpoint at the expected value, which is a characteristic of the distribution, and the PLDR1 at the ordering amount limit. And basically, this is a feature of the system itself. So the ordering amount limit is the cap of the amount you can order at each time stage. What was interesting to see, and this will kind of motivate the need to use simulators to assess the decision rule approximation later on. So what we see is that the storage and the backlog, which are mutually exclusive state variables, they are positive for the case where the demand in the third stage belongs from 0 to 5. So I had to say this figure corresponds to the storage and backlog policies, PLDR1 at the expected value policies at t equal to 3. So that's why we at the x-axis we see D sub 2, uncertain demand at the second stage, and then the uncertain demand at the third stage. We see that for the D sub 3 belongs to 0 and 5, both the values of the two state variables are positive. These values are being output by the model-based optimal policies for these two variables. This is impractical. It's impossible to have an inventory and a backlog at the same time. So here, so what's happening here? So when the tractable counterpart was basically derived, it was derived on the principle that, okay, feasibility for the worst case scenario will ensure feasibility for any other uncertainty realization. However, what we found, it may not be the case for optimalities, especially the case where the mutually exclusive state variables, at the worst case, it's not necessary to remain mutually exclusive at any other uncertainty realization. So what we decided to do is to implement two types of simulators to assess the quality, or to assess the quality of the model-based results. The first one is a folding horizon with no reoptimization. So basically, we only use the implementable policy, which corresponds to the ordering policy. And for the state variables, we use their definition. We do not use the policy, the optimal model-based policy. And the second simulator is the traditional moving horizon, or somebody, or let's say others use rolling horizon simulator, where and reoptimization is done at each time stage. Like for 8 time stages and given number of scenarios for each simulator. What we found is that not only the model overestimates the quality or the cost given by a given decision rule, it somehow may misrepresent the, between quotes, true solution quality of the approximation. In particular, if we compare the column, the model column, with the first simulator, we see that in the model, it is shown that PLDR1 with UX as a breakpoint is superior to PLDR1 as the expected value as a breakpoint. However, in the simulator, this is reversed. PLDR1 with a breakpoint at the expected value is found to be superior to PLDR1 and with a breakpoint at UX. Okay, by a small margin, but still this brings up the question, okay, can that happen with respect to an LDR? So just out of curiosity, like, can an LDR, which has a lower approximation quality than a PLDR, outperforms or beat the PLDR in a simulator, in the simulator? So to investigate that, what we did, we solved the problem over a range of ordering amount limit, UX 5 to 1. And what we see in the first figure for the model-based result, of course, like LDR is always inferior to PLDR1, and this is expected. But what's not expected is that we see in the first simulator, we see that for a certain values of the ordering amount limit, an LDR was found to be superior to a PLDR1, which is not expected. And the second point that we see is that the model-based result, it overestimates the inferiority of linear decision rules. This outcome, we use this outcome basically to advocate or to highlight the need to use simulators for your problem to assess the quality of what's known as look-ahead policy approximations. So now the second part in this computational study was basically motivated by an empirical evidence found in the scenario SP problem, where the modeling the uncertainty in more details in early stages is more attractive. Then we found a similarity between the number of scenarios in a stage and the number of breakpoints within each uncertainty in a given stage. For example, here, for this simple tree with 4 scenarios in stage 2 and 2 scenarios in stage 3, we end up with 8 overall scenarios and 8 overall finite adaptive decisions. Similarly, in the case of decision rule-based methods, if you have 4 linear segments in stage 2 which corresponds to 3 breakpoints. And we have 2 linear segments in stage 3. We'll end up with 4 linear partitions in the PLDR surface. So then, okay, we asked ourselves, then is it more significant to have higher uncertainty resolution or higher number of linear parts or linear pieces in a PLDR in early stages? To answer this question or to test this question, we use a modified transportation problem where we have a production policy and distribution policy, and we are maximizing the revenue. And to do that, to basically, we also use a moving horizon simulator, because as we saw early on, it's more like trustworthy. And the results are so basically in the moving horizon simulator, we use 200 scenarios, demand scenarios, and then we output the results based on the mean simulated cost and basically the mean profit change with respect to LDR and the mean simulation time. So for this experiment, we assume a superset for the breakpoints, and then we introduce some heuristics to choose these breakpoints and define the uncertainty resolution. And here, okay, here the main idea is that hybrid decision rules, they can offer a good trade-off between solution quality and computational cost with respect to the PLDRs and LDRs. Let's say with respect to what we call like kind of homogeneous decision rules. In the first case, we have to the left, it's a trade-off between LDR and PLDR1, and to the right, it's the trade-off between PLDR 1 and 2. Same thing can be seen with this additional HDR, which is trade-off between PLDR 2 and 1. However, the requirement to obtain this good trade-off between solution quality and cost is related to a good design of your a good design of what we call the non-increasing resolution. Because, for example, as we see in the right figure, a poorly designed hybrid decision rule may forfeit or may waste the added value of this tool. So now I will talk about quickly in 10-15 minutes about the steel making and continuous casting production problem. So we have iron ore basically passes through an electric arc furnace to be melted, and then it passes through another processing stage called argon oxygen carburization to add some elements that gives the steel its properties. Then it is passed through a ladle furnace, where the structure at the molecular level of the steel is kind of managed. And then at the end, it passes through a continuous caster to take the the required geometrical shape. And the problem statement is that given a production order, which is number of casts, the number of and processing sequence of ladles, which are the batch of molten steels in a cast, and the processing time of each ladle in each processing unit, which refers to the size of the batch, return an optimal schedule recipe that minimizes the worst case make span, satisfies strict production requirement, basically the continuous casting, because if the casting process is interrupted, then the whole product will be forged or will be wasted. And it has to be immune to uncertain processing delays. So here in this case, the uncertainty type is endogenous because it refers to the delay of the ladle I in the processing unit J. So if the ladle is not processed in that in this specific unit, the uncertainty will not be it will not exist. And we have in the adaptive optimization framework, we have the first stage decisions that are basically binary allocation decisions. It has to do with allocating the ladles in the processing unit J and allocating a cast C into an event point N. Now, soon after, we'll talk about the event N as a feature. And the recourse decisions are the timing decision, like start and finish decision of an event N in a unit J, and the start and finishing time of a ladle I in processing stage S. So the mathematical model was basically borrowed from the literature. It has basically typical processing constraint. That's a cast C is processed only in one unit in one unit J in a processing stage S. So in the case if you have a parallel units of the same operation, so the processing is done on only one unit. The zero weight states means that once a batch of steel is finished in a certain unit, it has to be right away moved to the next unit. Continuous casting requirements, the ladles should not be interrupted. The processing of the ladles should not be interrupted in the same, which belong to the same cast. And the perishability constraint that has to do with the storage of the ladles prior to the continuous caster. Here, the motivation behind the work has mainly to do with the unit-specific event-based continuous time representation. An event point is nothing but a time instant at which a task may start. In this case, the processing of a ladle. And these time instants are also decisions in the problem, so that they're being optimized by the time and finish decisions we saw earlier. Each unit has its own time grid or event grid, so that's why the name unit specific. And the timing of the tasks across sequential units are accounted for via special constraints, which we'll see them in a minute. So an example, this is a very schematic, simple example. We have like 3 units, processing units, and we have a 4-point event grid. So we see that the 1, 2, 3 grid in each unit is different. So they're not kind of correlated, or they're not the same. This decorrelation, it is the source of a superior performance of this continuous time representation in the deterministic setting. And this was very clear in a not comprehensive, but in an extensive computational study. And we found that it was not extensively explored in the context of adaptive optimization. So that was the motivation to do this work. But now the question is, the main question is, okay, how to construct your decision rule policies that will satisfy the non-anticipativity property. Because since the time grids are not the same in all units, it is not clear how these decision rules have to be constructed. So the idea that I propose is that we use these special constraints that was basically introduced for the deterministic setting. And these special constraints, they are the backbone of the continuous time representation. Like they are present in every scheduling application that implements this type of time representation. So it's not specific to the application, it's specific for the time representation. So I will use them as a tools, as a constructing tools to build the decision, to build the approximation. So the first set of these special constraints, I call them logical sequencing constraint 1, which has to do with previous events in the same unit. So let's say event 1 has to finish before event 2 starts, as simple as that. And then the second constraint is, I call it logical sequencing constraint 2, that has to do with the same ladles in previous processing stages. So let's say the ladle I has to finish processing. The ladle I will not start processing in processing stage S before it finishes processing in the previous stage. And then I had some problem specific temporal correlation given by the no intermediate storage policy. Basically, it's a type of storage policy. It belongs to a family of storage policies in process operation. And then the sequence of ladles within a cast. So part 3 is specific to the problem, I had to include them to ensure feasibility. But point 1 and 2, basically, they're it is fair to say they are they can be generalized to other applications. So as an illustration, I will go quickly. Okay, I will skip this part because of the time. So here I just illustrate how these tools work in practice. And here you have materialization constraints for the endogenous uncertainty. I just want to go to the scheduling technique. So the first technique is we call it a proactive robust scheduling technique, where we assume the entire uncertainty set of the processing delay, and we get the optimal policies, and these policies can simulate the schedule for any realized demand. So no rescheduling is needed. So let's say, using an example, we see in the right-hand side, if the realized uncertainty is, let's say, half the worst case delay, we see that, okay, we still get a schedule, but we can see from the gaps between the batch of processing batch, we see that it's suboptimal. In the case where the uncertain delay is equal to the maximum, so we see that there's no gap. So basically it's the optimum. That's what robust scheduling or robust optimization is doing. On the other extreme, we have something called deterministic reactive scheduling. This is it happens when someone will say, okay, why should I bother about uncertainty? What I will do is this: I will just solve a deterministic setting, and whenever there's a processing delay, it will invalidate your deterministic schedule, because this will disrupt the continuous casting in the continuous casting stage, which basically it will trigger a rescheduling. So you have to reschedule, you have to obtain a new deterministic schedule that will satisfy those strict requirements. So let's say, starting with an initial deterministic schedule, it gets violated by certain delay, so you have to do a rescheduling. And the downside of this technique is the large number of rescheduling events. So if you have a 2 cast 4 ladles, which is a very small instance, most probably have to reschedule the problem like 12 times. So here, like we did a quick experiment. So the experiment is divided into 3 parts: LDR design strategy, worst case scenario-based comparison, and an average performance-based comparison. So quickly about the LDR design strategy. So since this kind of construction technique was kind of new, we had to do this experiment to see like how do they behave. But what we found is that basically like complexity was not really necessary to, or basically the increase in complexity did not, let's say, pay off for this specific problem. So that's why we are using basically the simplest decision rule, linear decision rule type. For the worst case scenario-based comparison, so it is based on the idea that, okay, the robust proactive is simulated based on the worst case realization, and the deterministic robust deterministic reactive schedule is solved based on that too. For a 3 cast 8 ladle, we see that both of them have the same sequencing decision. In this case, the deterministic reactive was able to do better due to this ability to reschedule after each processing ladle. However, when we increase the instance size, so now we have 5 casts, 18 ladles, or 18 batches of steel. What we see is that, okay, if one, we have different sequencing decisions or different first stage decisions, which we know that for the deterministic reactive, they're not optimal because but the suboptimality of these first stage decisions in the deterministic reactive case is corrected. So that's why, let's say, for the 10% maximum delay, the solution quality is they are similar basically. However, when we have an 8-cast instance, so basically we increase the instance size, we see that the deterministic reactive schedule also failed to capture the optimum first stage decision for the worst case scenario, and now the suboptimality due to a suboptimal first stage decision was not corrected. So now we see that the robust proactive performance or quality is superior. But okay, it's not fair to say that deterministic reactive is not favorable, because the matter of fact is that the worst case scenario for all processes will rarely be materialized at the same time. So we are aware of that, and we are aware that the proactive robust schedule has a conservative mean-based performance. So to address that, what I did, I said, okay, fine, I will implement something called a hybrid scheduling approach. So it will provide a trade-off between frequent scheduling and conservative solution. The way it works is that I will adapt a truncated uncertainty set. So I know that the maximum delay is delta max for in a processing unit J, but in the model, I will assume that the maximum delay is delta TR truncated. And if when I run the simulator, if the realized uncertainty is larger than the delta J truncated, because in real life it can be larger, my assumption assumes that it cannot in the model. If this happens, this means that the current schedule is invalid. It's not guaranteed to satisfy the continuous casting requirement. In this case, I will trigger a rescheduling. So this approach, what we aim to achieve using this approach: reduce the conservativeness of the robust proactive schedule, and basically reduce these frequent rescheduling events of the deterministic reactive scheduling. So to see how does it work, we quickly, in 5 minutes, I ran this experiment based on 3 different distributions. And here the main element of the distribution is the skewness. So right skewed, uniform, and left skewed, or the asymmetry, some people may say it. And here we have some like parameters for the experiment. I use like 100 sample scenarios for the simulator. And here what we see, this figure, it outputs the mean change in make span with respect to the deterministic reactive scheduling for the 3 different distributions. So one thing we notice is that for large value of the uncertainty support, or the truncated uncertainty support, we see that on a mean-based performance, the hybrid schedule is basically comparable, if not superior, to the deterministic reactive make span. And this is achieved while implementing a lower number of rescheduling events. So you're doing less efforts and you're getting better solution, better output. And why does this happen? Because when you incorporate part of the uncertainty into determining your allocation decisions, your first stage decisions, you'll have a better chance to exploit this added value in your recourse policies, adaptive policies. And this is with the main limitation of deterministic reactive make span. And another observation is that, which is expected, as the asymmetry or this skewness moves to the right, the conservativeness of the larger uncertainty support decreases. So we see that the curves are kind of bending towards the bending down as we go from left to right. This figure, it shows the change in make span with respect to the robust scheduling, robust proactive scheduling method, but as a function of the scheduling events. So here, what we see is that regardless of the type of skewness in the distribution, for a for a small number of rescheduling events, you have opportunity to kind of reduce the conservativeness of the robust scheduling method. And the idea of this basically this results is to give kind of insights to guide the decision making in the process, and basically to advocate or to present the idea of the hybrid scheduling approach as a competitive alternative to both deterministic reactive and robust proactive scheduling methods. So basically, to conclude, the four main takeaways, if I would say, one, decision rule based methods as a solution technique for optimization under uncertainty problems. When we implement such a technique, it is important, or it is crucial to assess the model-based approximation, or to assess your assumption in a given simulator. Basically, the simulator is specific to your problem. The third point is the impact of the first stage solution quality on the overall optimal cost. And this impact should not be underestimated. Basically, even if your first stage solution quality is low, even if your the course policy is of high quality, if your first stage solution quality is low, it will kind of limit the room at which you can improve your optimal cost. And okay, throughout the work, I am aware that future work may include investigating decision rules for discrete decisions, and mainly explore methods where the approximation structure is not determined beforehand. Well, I would say two main assumptions in the current decision rule literature is that the form of the approximated policy is determined a priori. So whether it is LDR, piecewise-linear decision rule, or quadratic. And two, the uncertainty is assumed to fall within a closed convex form. So one research direction is to kind of relax to work to relax these assumptions, or something currently known as basically to learn the policy as you determine as you solve the problem. And yeah, and thank you for listening.